Hi, this is Kevin Ega. Welcome to Math 250, Calculus 3. Welcome to these lectures given online. Hope everybody is safe and found a place to be comfortable, whether you're with family or friends, with both. We'll try to get as much done these weeks before we return. Sorry I'm not with you in person, but hopefully these lectures on video will be useful to you. So, one thing to say, these lectures will not necessarily follow the timeline that we've been that we would normally have. Normally, for instance, I would meet with you for 50 minutes each time. Some of the material that I have is longer than 50 minutes. Some of the material I have is shorter than 50 minutes. Normally, this would be broken up according to days. I'll try to give you a little bit of indication as to how that would work. So today, for example, 13.2, we've actually talked about a lot of 13.2. I just have some things to say about 13.2 today. Normally, today we would do 13.2, the rest of 13.2 rather, and a little bit of 13.3. So, but this lecture on video is only going to be about 13.2. So you have to read this, watch this video, and then watch a little bit of the next video if you want to really be exactly according to the schedule that we would normally be on. So this is line integrals 13.2. By the way, I'll also mention when you should be doing homework and so on, when you have enough information to do the homework. You can do this at your own pace, of course. You don't have to follow the specific timeline, but I recommend following something close to the timeline so you don't get too far behind. All right, so last time we were talking about 13.2 line integrals. And recall that I said there are three types of line integrals: integral of f ds, integral of f dx, and integral of f dot dr. So you have a curve here, C. Okay, it's broken up into lots. I imagine it's broken up into lots of little segments like this. And for each segment, I just take, for instance, in the first type, I just take integral of f ds, the value of the function. For each of these segments, I take the value of the function somewhere on this segment, like here, times this length ds. And I do that for each of these segments and add them up, and that is the sum that we take. The limit as we get finer and finer of a subdivision here will give us this integral. Okay, so last time, that's what we did. We also did this, integral of f dx. It's almost the same thing. Again, you divide your curve into these segments. For each of these segments, you have the value of the function times dx. So the idea is it's going from this point to this point, but I don't take this distance. I just take the change in x, which is this. Okay? Multiply the function times that, add it all up. That's this integral here. Similarly, there's the same thing with the integral of f dy, where you just, instead of multiplying by f times this, you're multiplying by dy, the change in y. Okay. So those are the kinds of integrals we talked about last time. We talked about what they mean and showed this picture and how to compute it and all of that. So today we're going to talk about the third type of line integral, this one. Okay, integral of f dot dr. This one is maybe the most complicated for me to explain, but it's actually not any harder than doing these other integrals. In fact, these integrals are going to be, well, let me put it this way. Remember when I said the integral of f ds, those integrals often are difficult integrals to do because this ds involves taking a square root of things that you add together. Actually, these other two don't have that problem. So, as you'll see later on, even though this one, when you put in fairly innocuous looking functions, pretty easy looking functions, and the curve is pretty easy, this one can often give you an integral that's very difficult to do. These other types, that's not the case. I mean, they might still be hard if, for instance, this vector field or this function is hard, or if this curve has a really complicated description. But that's true in any problem. If you have hard functions to deal with, then the answer might be hard to work out. But if these are easy, then this integral will be an easy integral, whereas here the integral might very well be difficult. Anyway, so that's good news about this one. This one is it's not going to make things any harder than it was before. It's also, as we'll see, one of the most useful of these three. It's actually the most useful of these three. So even though this will take the longest to describe, it's actually the most useful one. In this um, kind of integral, instead of a function of x and y, that's a scalar function that's like this, instead we have a vector field. Capital F here is a vector field. So we imagine this vector field everywhere here. Okay. And what does this do? This takes this vector, well, for each of this segments on this curve, we break up the curve into segments as before. For each of these segments, we're going to take this function f, okay, this vector field f, and dot it with dr. What is dr? Dr is this vector like this. So it looks like ds. ds goes from this point to this point, but ds is a scalar. ds is a distance, whereas dr vector is a vector. It goes from here to here. Okay, and you take the dot product of f and dr. That's going to give you a scalar. And so each of these little segments here, I'm going to take f dot dr, and then that's going to give us these numbers, and add up all these numbers. Okay, and that gives us this. At least it gives us this in the limit where this subdivision gets finer and finer. So what is this like? Well, so let's review the dot product here. So if you recall, the dot product of f and dr is the length of f times the length of dr times cosine theta. Okay. Here's a picture, dr and f here. I'm aligning dr to the right here, horizontally. And if you take this vertical line from f, dropping it down to dr, so it's perpendicular to dr, then you get this right triangle. This is the length of f times the length of dr times cosine of this angle. If you look at this right triangle, this length here is the length of f, and so this length here is the length of f cosine theta. So you see length of f cosine theta. I take this length here, multiply it by the length of dr, and that's going to be the dot product. In other words, what I should do is I should look at this distance. What is this distance? One way to imagine this is you imagine a light source that's right above, and it's going to make a shadow here. This is going to be this shadow is going to be this length. It's going to be times dr. If you recall, this is what's called the scalar projection, or the scalar component of f in the dr direction. So back in chapter 9 in 9.3, 9.4, somewhere around there, 9.3, they talked about the scalar component. Okay, that's what this is. The idea is this: f has some amount in this direction and some amount in this direction. This direction here doesn't count. All that counts is this one. I'm going to look at how much f is in this direction multiplied by dr, and that's the dot product here. All right, so going back to this picture here, this integral, I chop up this curve into lots of little pieces. Each piece, I look at f dot dr. I don't care about f in this direction or this direction. I just care about f in this direction. So if f has this piece and this piece, then this piece doesn't matter. I just look at what f is in this direction here. Okay, and then I do that. That's going to be a little bit here, and I just add it up over all of these little pieces. Okay. By the way, this is not going to be the area or volume of anything. Okay. Remember when you took the integral and you first learned about integrals in your calculus class, calculus 1, you were told that this was the area under a curve, and I've been trying to encourage you to get rid of that notion. The fact is, this case here, the integral of f dot dr, really is not an area or volume of anything. So instead, I've asked you to think of integrals, different integrals, as adding up lots of little pieces, and that's really the way you want to think of this. Okay? So it's not going to be an area or volume. This is going to be adding up lots of little contributions from each of these little segments here. Okay, so that's what these line integrals mean. Let's talk about how to compute line integrals. So let's recall from last time the integral of f ds. How do you compute it? Well, the trick is you don't compute it here. You instead compute it here. What is this? This is t. This is a number line, and here is the parametric equations. More specifically, it's the vector function that goes from t to this plane. Okay, and we call that r of t. And so when I have a parameterization, this is the equation of my parameterization. And the idea is, instead of integrating here, let's integrate it here. And the idea is integral of f ds. Well, I just for each little segment here, I first do this, and then I do whatever function it was. So I plug this in and compose it like this. And instead of writing ds, I put ds dt times dt. The dt's, of course, cancel, and this is as before. This is just how we just change coordinates from ds to dt. And ds dt, that's the speed. And so this is the magnitude of r prime of t. Okay, so remember how this worked. So instead of integrating on ds, you're integrating on dt, but I just have to stick this extra piece in here. Likewise, integral dx's, it's the same idea. Instead of integrating here, you integrate it here. And so this is integral in t. And instead of dx, I put dx dt times dt. Just take the derivative of the x component of here and stick that in here. So again, this is an integral on this. And I just have to stick this extra piece in. So it will not be a surprise, I think, that it's the same approach for these kinds of integrals. Okay. In this case, you've got an integral of f dot dr, where f is a vector field. And again, instead of integrating here, we're going to integrate it on t. So t is, again, going from wherever we start to wherever we end. Plug in your parametric equations into your vector field. Oops, this is supposed to have a vector on it. And dotted with dr dt times dt. The dt's cancel, and this is the same as this. But dr dt is just a derivative of this vector valued function. And then you take the dot product, and then this is just an ordinary integral. All right, so let's look at an example. Now let's consider this curve here, given by these parametric equations: x equals t squared, y equals t cubed. T goes from 0 to 2. And let's say we have to compute this line integral. And a line integral on this curve C of f dot dr. Here the vector field is x squared y comma x cubed. So that's our vector field, dotted with dr. Okay, so how do we do this? First of all, we take our parametric curve here, x equals t squared, y equals t cubed. We turn it into a vector valued function. Take the x component here, y component there, put it into a vector, as in chapter 10. Take the derivative of t squared, derivative of t cubed. You have this vector field, x squared y comma x cubed. I just plug in, wherever I see an x, I plug in this. Wherever I see a y, I plug in that. So there you go. There was an x there and an x there, so I just plug in t squared both places. Plug in t cubed into there. Multiply it all out. You should get t to the 7th comma t to the 6th. I won't work it out for you. You should be able to do that yourself. And then, so that's what we got. R prime, and f. Integral of f dot dr, you just put in f here, r prime here, dt. This is a dot product. So take the dot product, multiply the x components, multiply the y components, add them, you get this. Do a little algebra, do a little calculus, you should end up with that. Okay. You should, by the way, check to make sure this makes sense to you by pausing the video and working this out for yourself. So go ahead and do that right now. All right. So the next one is very similar here. This curve is given by this parametric equation here. And I'm asking you to compute this line integral, negative 3y comma 3x dot dr. So actually, before we do this problem, you should know what this shape looks like. We don't need to know what the shape looks like in order to do this problem, but just verify that you do know what this looks like, because just it's good to keep up with their practice and recognizing the kinds of parametric curves that you should know. All right, everybody know what this looks like? It looks like a semicircle. Well, so cosine of t sine t, that's the unit circle, multiplied by 2, that's going to be a circle of unit of radius 2, but this doesn't go from 0 to 2 pi. 0 to 2 pi would make it the whole circle. This stops at pi, so that's just going to be the upper half. It's going to stop before it goes any further. So this is going to be the upper half of a circle of radius 2 around the origin. Anyway, that's not needed to do this problem, but just figured I'd keep you on your toes with that. All right. Now, here you've got a curve. This is our curve C. You're doing this integral here of this dot dr. Go ahead and do this problem and pause the video, and then start it again when you're ready. All right, go. All right, here's the answer. Here is r. Take the derivative. Plug in the x and y into f. You should get this. Integral of f dot dr is this dot this dt. Integrals from 0 to pi. Multiply it out, add, you get 12 sine squared t plus 12 cosine squared t. Sine squared plus cosine squared is 1. So this is going to be integral of 12 dt from 0 to pi, which is 12 pi. All right, hopefully all of you got that. The same thing works, by the way, if you have a line integral in 3 dimensions. In the 3 dimensions, the vector fields are now 3-dimensional. Your parametric curves are now 3-dimensional. So here's a parametric curve that's 3-dimensional. It's got an x, y, and z component. Here's our vector field. It's got x, y squared, z, and x cubed. You've got 3 components here, the x component, y component, and z component. That's why it's 3-dimensional. The integral of f dot dr is similarly, you just put f here with plugging in, of course, x, y, and z into these things, and dotted with the derivative of this. The derivative of this is, of course, this. And multiply, add, you get this integral, okay, which you can, of course, do. So anyway, the integral of f dot dr, it works exactly the same way in 3 dimensions. All right, so now you know all of that. There is one little last bit that I wanted to talk about, and that is the relationships between different kinds of integrals. So we had these kinds of integrals f ds and integral f dx, and today we talk about the integral of vector field f dot dr. And I wanted to mention that these are not actually all really different. In fact, the last two are really closely related. They're actually the same thing. So what do I mean by that? If you have a dr is actually this dx comma dy. So this vector here is dr, and it's got the x component dx, y component dy. And so this integral here, this was the first example that we did, dot dr, I can actually write it as this times dx plus this times dy, like that. So, more generally, if we write f, their vector field as got an x component p and y component q, I can rewrite this f dot dr as this kind of integral. So an integral of f dot dr is actually an integral of p dx plus q dy. So if you break it up into 2 integrals, these are both going to be integrals of the type that, the second type, the integral of something times dx or something times dy. In 3 dimensions, if you've got an x, y, and z component, p, q, and r, similarly f dot dr is going to have p dx plus q dy plus r dz. Okay. Conversely, in the other direction, let's say I have a line integral of this type, some function times dx. You can define this vector field. Just take this and put it in the x component and put 0 in the y component. Then f dot dr will be this. Same works with, you have an integral dy and just put it in this instead. In 3 dimensions, if you have an integral f dz, then of course this is going to have an x, y, and z component. You just put it in the z component. It all works exactly like this. So the point is, integral of f dot dr and integral of f dx and f dy are all really the same thing. I can convert them from one to each other. They're the same thing, just different notation. There is also a relationship between the integral of f dot dr and integral of f ds. It's not as close of a relationship, but we do have this. If you have, remember t is the unit tangent vector, and t is points in the direction of r prime. So you take r prime, make a unit vector like this, or what's equivalent is you take dr and make that a unit vector. It's the same thing as this. It's just this is dr dt, dr dt, cancel the dt's and you get this. In other words, we get t is the dr, turn it into a unit vector. Remember that the length of dr is just ds. Remember, this is ds here. The dr vector points in that direction. So another way of doing this, you just multiply by ds here. You get dr equals t ds. Dr here is this vector, and this is writing a vector in terms of its magnitude and its direction. Magnitude times the unit vector. So here's the magnitude, ds, times the direction, with the unit vector in pointing in that direction is t. Actually, of course, this is not exactly the t. T is supposed to be tangent to this, but and in the limit, as you get smaller and smaller, finer and finer subdivisions, that's the direction that's going to be pointing. So dr is t ds. And here we go. This is integral of f dot dr can turn into integral of f dot t ds. And now, just thinking of it this way, f dot t helps us understand what this is all about. F is this vector field. T points tangent to this curve. And if I do that, then I'm going to get f dot t. Remember, f dot t is the component of f in the t direction. So normally the scalar component would be f dot t divided by the length of t, but t is a unit vector, so that's the same thing. The length of t is 1. So f dot t is just how much of f is pointing in the direction of t. And that's how we get, for each of these segments, we just look at f dot t. Now there's the component of f in the t direction, how much the wind is helping you, basically. You multiply it by ds, and you add it up over all of these pieces. Okay. This kind of puts a more solid foundation to what I said at the beginning as to what this integral of f dot dr meant. What it's doing is f dot t, the component of f in the t direction, the part of the f that's pointing along the curve, times this length, add it all up, and that's what this is. By the way, this is a terrible thing to do for computation. I would never do this in order to compute this thing. After all, as I said, these integrals tend to be hard. These integrals tend to be easy. This is not what I do for computation. Rather, this is what I do to help understand what this means. Okay. All right. So there's one last thing I wanted to talk about, and that has to do with parametrization. So remember back in chapter 10, I talked about the difference between what I call geometry versus physics. Whenever you have a curve, there are two ways to think about it, especially if we're going to parameterize the curve. In geometry, we just care about the actual set of points, the shape of the curve. Whereas in physics, we actually care about when we are at different places. So here I've got two curves. It's the same set of points, but here I put tick marks to indicate when I'm at various places. So t equals 0, t equals 1, t equals 2, it's, and so on. Here t equals 0, t equals 1, you see I'm at different places, and maybe I go through it faster in this curve than on this one. So in geometry, I would call something geometry if it doesn't depend on the parameterization. In other words, if it's the same for both of these. Or physics, I would call it physics if it depends on the parameterization, where you might get a different answer for this one as this one. So the question is, what are line integrals? Are line integrals part of geometry or physics? And the answer is geometry. Well, let me show you what I mean. So in this case, I'm looking at integrals of f ds. We can reparameterize. So here's one way to think about what's going on with different parameterizations. In one case, I've got this parametric curve, r of t, and the other one's going to be the same thing, except that the times are going to be different. So let's imagine we got this function here that turns time for one curve into time for the other curve. That's h of t. I just plug that in here, and that will tell us, give us another function, call it p of t. Now, now the book actually goes through and computes both of these, and both using p and using r, and you use things like the chain rule and things like substitution and integrals. Actually, you can follow that, but I'd like to show you the picture here. Here's the curve. Here is 2 tick marks. Here is ds. That's this length. We're going to multiply f times ds. Now here's the thing. These tick marks will be in different places for these different curves, depending on the parameterization. But when you have more and more tick marks, you're going to fill up this whole thing with tick marks everywhere. And we're going to have the value of the function times these distances. It's going to be the same whether or not you have this one versus that one. So just by looking at this picture here, you can see that this integral is going to be the same as this integral. Okay. Same argument works for these other ones too. Okay, it's the same idea. Here multiplied by dx, here multiplied by dr. Here you got a vector field dot dr. It's basically, given that you have this this picture here, it's going to be basically the same. So these are going to be independent of the parameterization, with the exception of one little thing, which I'd like to talk about, and that's orientation. What is orientation? Now, orientation is a pretty simple idea. It's which direction you're going on the curve. So let's say you start from here and you go this way. I put a little arrow here to indicate which way we're going. Okay, and here we're going the opposite direction. We're going from here, ending in here. Okay, and so I put the arrow that way. This is called orientation. So these two are the same set of points, but they're opposite orientations. Okay, so if we've got an integral of f dx, you notice that when I'm traversing the curve in this direction, dx is this, whereas in here dx is that way. So it's this minus this. Here it's this minus this. In this case, dx is positive. I'm going to the right. Here dx is negative. I'm going to the left. And so when I add up over all of these things, the answers to these are going to be exactly negative of the answers of these. When I add them all up, I'm going to get an overall minus sign. So the integral of f dx is going to be opposite of the integral of f dx when I change the orientation. If c1 and c2 are the same curve but the opposite orientations, then you just put a minus sign. Okay. Here's what you get. Integral of f ds, so that doesn't change at all. Okay, remember ds is this length. It's going to be the same whether you go this way or that way. But dx changes sign. dx, how far x is changed, is going to be positive in one direction, negative in the other. Same with dy. dr, similarly, dr is going to be this vector going this way. In one case, it's going to be the vector going the opposite direction. In this case, you're going to get a minus sign. So these change sign. This one stays the same. Okay. All right. So now you know the meaning of the integral of f dot dr, this kind of line integral. Okay. You now know how to compute this kind of line integral. Okay, if I give you a curve and give you a vector field, you should be able to compute this. You should know how to convert this kind of line integral to the other kind of line integral, p dx and q dy, like this, and how to go back. The relationship between this and the integral of f dot t ds, so an integral on ds, and the point is how to use this to understand better the meaning of this integral. You should know about independence of parameterization. All of these are independent of parameterization, except that some of them depend on orientation. All right, so that's what we've covered today. You will now be able to do your homework that's due on November 16th. We will do section 13.3 next time, the fundamental theorem of calculus for line integrals, just to give you an idea of, to give you a little bit of a preview. The fundamental theorem of calculus is, of course, important. It's called fundamental. It looks like this. Integral from a to b of f prime of x dx is f of b minus f of a. It says the integral of the derivative. Well, the integral and derivatives don't exactly cancel, but it's not like this is f of x. Rather, it's f of b minus f of a. Okay, and the point, though, is that if you have a derivative on the inside and an integral on the outside, that the result is just the value of the function at these uh, boundary points. It doesn't depend on the value of f anywhere in between, which is kind of remarkable. One of the uses of this, in fact, the main use that you've made of this, is to compute definite integrals. For instance, if you wanted to integrate x squared dx, for example, the thing to do is to recognize that x squared is the derivative of something. It's the derivative of 1/3 x cubed. And you just plug in b, plug in a into 1/3 x cubed and subtract. Okay. Now, we have learned about several different kinds of derivatives, like partial derivatives, directional derivatives, gradients, and several kinds of integrals. Double integrals, triple integrals, line integrals. And the question is there a version of the fundamental theorem of calculus for these kinds of things? And the answer, of course, because you see the name of the chapter, is yes. For line integrals and gradients, there is a fundamental theorem of calculus. So that is what we'll cover next time, and I will see you then.